All right. Hello, class. Mr. P here. Hazel's right here. Um, you might notice that I'm shifted about 2 feet over from where I normally sit. That's because Hazel had a giant uh-oh yesterday right there. Right there. And luckily it wasn't on the couch because I just got this couch and it's fairly expensive. Um, so it was, but oh my gosh, when Hazel throughout her life, she gets sick about once per year, and during that week of time, and maybe once every 2 years, and during that week or two where she's sick, she just destroys everything. It's just like I have to literally put her in an enclosed space, and she cannot get out because if she gets out and you don't watch her, she will have an accident somewhere and destroy that. It'll never be on a place that's easily cleaned. It's always on something that's like a pillow or something that you can't get that sort of thing out of. It's maddening. So now I'm just thinking, I'm like, should I just throw it? Should I just throw this rug out? I don't know. I might. Hey, Chris. Hey, Jackson. Hey, Sofa. Hey, Christian. Hey, Spicy Pepper. So I'm coming at you today with a paper 3, Ivy Physics SL paper 3. This is the November 2019, and I'm going to be doing questions 2 and 6. So let's get right into it because I'm a little bit behind already. So here, oh, that's question 1. All right, question 2. It says the resistance R of a wire of length L can be measured using the circuit below. And one of the things I want to point out is that this right here is a resistor. Okay, that's the IB symbol for a resistor. In one experiment, the wire has a uniform diameter, D equals half a millimeter. The graph shows the data. All right, cool. The gradient of the line of best fit is 6.3 ohm meters. Estimate the resistivity of the wire to an appropriate number of significant figures. Okay. So we have the equation that R equals rho L over A. Okay. So we have R on the vertical axis, and we have L on the horizontal axis. So the thing that multiplies the horizontal axis is the slope. So the slope equals rho over A. So that means that rho equals slope, and it gives us the diameter, right? Slope times the area, which is going to be pi d squared over 4. So that's the area of the circle in terms of diameter. Okay. So one of the things I can see is notice how the diameter is given to 3 significant digits, 0.500. Okay. And furthermore, the slope is given to 3 significant digits. Okay. So what that means, when you're doing a calculation like this, basically you're going to use the number of significant digits that is the least amount. Okay. So, for example, if one of these only had 2 significant digits, then my answer for the resistivity would only have 2 significant digits. Okay. But because both of them have 3, I'm going to give my answer to 3 significant digits. So I have 6.3 times pi times d squared, so 0.5 times 10 to the minus 3, that quantity squared, over 4. And that gives 1.24 times 10 to the minus 6 ohm meters. Now, notice that this is 3 significant digits. My actual calculator is giving more than 3 significant digits. You can see that. So I rounded it to 3 significant digits because that's what's appropriate. All right, part 2. Explain by reference to the power dissipated in the wire the advantage of the fixed resistor connected in series with the wire for the measurement of R. So, a little bit thrown off by this question. So the power dissipated in the wire is going to be I squared times the resistance of the wire. So we can see that the power is related to the current. Okay, so I would say that we want to keep the power dissipated by the wire to be small. And the reason is that if the power dissipated by the wire is not small, then the temperature of the wire is going to be fluctuating, and resistance depends on temperature. So we want to keep the current as small as possible, so we could do that by the current low. All right. Where was I? I got lost here. Part B says the experiment is repeated using a wire made of the same material but of a larger diameter. So larger diameter means bigger area, which means less resistance at each length. So your line is going to maybe look something like this. Okay, less of a slope. So that's pretty straightforward. Okay, so the next question I'm going to do is question 6. All right, here's question 6. An ideal gas consisting of oh, hey, Sebastian, you're in the wrong lesson. An ideal gas consisting of 0.3 moles undergoes the process A to B to C to D. A to B is an adiabatic expansion from the initial volume V sub A to the volume 1.5 V sub A. BC is an isothermal compression. Pressures at C and D are the same as that in A. The following data are available. So A part I says, show that the pressure at B is roughly 130 kilopascals. So when we have an adiabatic expansion, you have P initial times V initial to the 5/3 equals P final times V final to the 5/3. Okay? So our P initial is the pressure at A, which is 250 kilopascals. Then we have V initial to the 5/3. the final volume, okay, so we can see that the V naughts are going to cancel, and so we're going to get that P final is equal to 250 divided by 1.5 to the 5/3. And that is 127 kilopascals. Sub C. Okay. So let's see here. All right, so we're going to use the ideal gas law. So V sub A over V sub C is going to be equal to nR T sub A over, so this is the ideal gas law right here, and then nR T sub C over P sub C, like that. Hang on a second. I'm trying to figure out if I'm actually... I think I can actually calculate the volume at A, can I? So the volume at A is N, which is 0.3, times R, which is 8.31, times what am I missing here? Okay, I'm not going to use that method. So the NRs cancel out. The pressure at A is the same as the pressure at C. So VA over VC is equal to T sub A over T sub C. Now, how does the temperature at A compare to the temperature at C? I'm going to come back to that because it's a 1-point problem, so it's very simple. But for whatever reason, I'm like blanking on what equation I need to use. So I'm going to come back to that. All right, part B. The gas at C is further compressed to D at a constant pressure. During this compression, the temperature decreases by 150 Kelvin. For the compression, CD, determine the thermal energy removed from the system. So the gas is compressed here. Okay, so work is done to compress the gas. So what is the work done on the gas? All right, the work done on the gas is going to be P times delta V. So the pressure is 250 times 10 to the third. 250 kilopascals. The change in volume is, I got to subtract these two numbers. Okay, so subtracting those two numbers is going to give a volume of 1.5 times 10 to the minus 3. So I have 250 times 1.5 equals 375 joules is the work done on the gas to compress it. Okay. Now, if I use the first law of thermodynamics, it says that the change in internal energy is equal to the heat added to the gas plus the work done. Okay. Now, the internal energy can be written as 3/2 PV. So that means that the change in internal energy is 3/2 times P times delta V. Okay? So we have 3 times that. The change in volume is, well, actually it's compressed, so it would be negative, wouldn't it? So it would be negative 3/2 times 250 kilopascals times 1.5 times 10 to the minus 3. And that equals Q plus 375. Subtract the 375 over, and we get that Q equals minus it's going to be minus about 938 joules. So that would be the thermal energy removed from the system, so the heat. That's Q. Explain why the entropy of the gas decreases. So basically, if you have a smaller volume of gas, okay, so remember, entropy measures disorder, and if you have a smaller volume of gas, then what that means is that there are less possible positions for the gas molecules to have. Okay, well, actually, and so if you have less possible positions for the gas molecules to be in, then there's less disorder. Okay, basically, it's closer to a solid. Another way to see it is to notice that delta S equals Q over T, and thermal energy is removed from the system, so that means that the entropy had to go down because Q is negative. State and explain whether the second law of thermodynamics is violated. I would say no, because the second law of thermodynamics says that the total entropy of the universe must increase. Okay, and but that doesn't mean that a single thing can't have its entropy decrease. So the entropy of the gas decreased, but the entropy of the rest of the universe went up by at least that amount. Okay, so it's not violated. So that's the end of option B. I'm still a little hung up on this problem, but I'm just going to have you guys look up the answer yourself. There's only 4 of you watching, but it's just, this is the 2019 November exam, and I don't want to bore you guys by just sitting and thinking about it for a second. The answer's not jumping out at me. So if you're curious, look up the answer yourself. If not, maybe I'll talk about the answer to that question tomorrow briefly. All right. Have a great afternoon, and I will see you tomorrow.